Okay, next is clustering. So we talked about feature transformations and how to derive vector data or feature data. Now let's talk about how to get clusters out of those feature vectors. And well, clustering, first of all, is a classical unsupervised task, and the patterns you want to extract here is, since you know nothing about the data, you are interested in grouping the data into meaningful clusters, groups, and that means typically meaningful means here similar objects. So you want to find groups of similar objects. Here the picture here on the right hand side, you see that there are obviously two groups of points standing for some complex objects maybe, and you see that the points within the clusters are more similar to each other than to other clusters. So the green guys are more similar to each other than the purple ones, and vice versa. So obviously in that case, kind of concept of similarity is important. Well, instead of similarity, we talked about it before, usually you use distance or distance measure, and the problem in general is that since it's unsupervised, you have no clue how these patterns look like. So what are the characteristics of your groups? Yeah, so take a look at this one here. Here are 4 different data sets with completely different groupings of data. So here you have 3 Gaussian distributions that somehow overlap each other, as it is the case with a mixture of Gaussians in general, typically. Here, for example, you have different groups that have a very arbitrary shape, like these sausages here. Let's call it sausage maybe. Yeah. So here 4 sausages that are somehow clusters. In this case, you have more spherical clusters, but the similarity within each of the clusters are very different. So here is here in this case, the similarity within the cluster is very, very small. So the distances are very small, the pairwise distances. Whereas here, for example, or here, it's much less. Yeah. So you may have completely different characteristics for your clusters, and typically it's not 2-dimensional. So if you have 2-dimensional data, you can look at it, no problem. But if you have 10-dimensional data or even 100 or 1,000-dimensional data, of course you have no clue how these patterns look like and what kind of patterns you should search for. Yeah? So we have to be clear that we have no clue about the characteristics, how many patterns, how many clusters are there, what is the data distributions of each of the clusters, what shape do they have, is there some noise? So we have, in this example, we have also probably noise points around here or noise points around here. So this one is probably a noise point which shouldn't belong to any of the clusters. Yeah? So we have no clue about noise, of course. Typically there is a lot of noise in real world data, but anyway. So we have to be clear that since we don't know anything about it, in order to find something, we have to make a lot of assumptions regarding those questions in order to find anything. Yeah? And each method, so this is again one of the reasons why there are so many methods for clustering out there, because each of the methods typically assume a given pattern. So the so-called cluster model, typically defined implicitly or explicitly by the input parameters. And what those methods basically do is they search for those patterns, and very often they find those patterns, or if those patterns are not there, they simply don't find those patterns. It doesn't mean that there are no clusters. It just means that those patterns are not there. So you can think of clustering algorithms more like search methods that look for particular patterns, and to know about the patterns that a particular algorithm looks for is of course very important. So here in the remaining part of this subsection, there are some paradigms, some cluster models that look for different patterns. We have talked about that in KDD1. So partitioning methods like k-means, k-median, they typically try to construct k partitions. Usually those clusters have spherical shape, and these partitions should be optimal with respect to some fitness function. Typically it's compactness here. Yeah? So the important concepts here, as you may remember, is cluster representatives. How should we model the cluster or represent a cluster? K-means use the mean, K-median the medoid, and so on and so on. And then the cluster criterion, like compactness, which is, for example, the criterion of K-means, and it uses the sum of squared distances of all cluster members to its representatives in order to measure this compactness of clusters. And it tries to optimize the compactness of clusters here. Yeah? And you probably remember the basic scheme. You start off with random models, random representatives here, the red one and the green one. And in the first step, you assign each point to the closest representative. So all the green guys go to the green one, all the orange ones go to the red one. And then you update the cluster model. In that case, it means you update the cluster representatives. So the new mean, we think that, we assume that it's the mean, the cluster representative. So the new mean of the green ones is the green here, and the new mean of the orange one is the red one. And then again, you reassign points to the closest representative. So you see this one here that has been red now goes to the green one. So it's going to be green. And this one here was green, and now it's going to be red. Yeah? And then again, you update the model, and then reassign and update and reassign and update. And at some point in time, all points are not reassigned to any other, to some other cluster representative, but stays stable, or stays stable. And in that case, the algorithm stops, and you have some partition, or you have K partitionings. So K is the only input parameter of these methods, and those methods always return K clusters, nothing else. Yeah? Even if there are no clusters in there, they return by construction, by design, K clusters. Always keep that in mind. A slight variant here are the probabilistic methods. The idea is not to use a simple model like the mean or some other representative, but use probability functions or distributions, typically Gaussian distributions. So you want to now fit K Gaussian distributions to the data. That means in the end you represent each cluster by the mean again, and now the standard deviation, so that you have probability distributions. And now your fitness function is the log likelihood of each point being generated by these K distributions, because each point now belongs to all the K distributions with some probability. And that's why the whole thing is a fuzzy clustering. Yeah? Each point now belongs to all clusters, just with some certain probability. Yeah? And of course, you can get a hard clustering by just maximum likelihood decisions. So assign each point to the cluster with the highest probability. So then you get a hard clustering. Popular methods especially include the expectation maximization method, and the basic algorithmic schema is very similar. The two-step approach by updating the model, reassigning the points. In that case means computing the probabilities, updating the models, the Gaussians, and so on and so on. So it's very, very similar to K-means in these variants. Then we had the density-based methods, which use a completely different approach. So they say that clusters are regions of high point density. So you see here, for example, this light blue cloud of points. They are, as long as you are within this area here, the point density, so the pairwise distances, for example, are quite high. The same holds true for the dark blue area and for the green area here. And what separates the clusters is the regions of low point density. So you see that in between those three clusters, there is a region where the point density is very low. So the gray ones here also are points that are in a low density area. So they are implicitly regarded as noise. Yeah? So that is the nice point, the nice thing here, that DB scan, the density-based methods, typically have an implicit model of noise points. Yeah, so there are different concepts of point density, because density obviously is the key concept here, and there are different definitions, like the minimum number of points in a volume, like in dbScan, or some probability density with respect to a certain type of distribution, typically Gaussian again, which is, for example, used in DENCLU. So dbScan grid clustering usually uses a minimum number of points in a volume, and also mean shift, which uses a common mode within a volume, can be seen as density-based methods. There are completely different algorithmic schemata available, mostly differing in different concepts of volume, density tests, and connectivity. And we talked about the popular methods already here. So, and there is some kind of, because I mean, so here these probabilistic and partitioning methods is just one big family, then the density-based methods is another big family, and there's something in between, which is which are the spectral methods. So in that case, the data is modeled by a similarity graph, the general idea is to partition the adjacency matrix like a min-cut problem. This problem, however, is in general NP hard to find really the optimum cut here, and the workaround to escape from this NP hardness is, well, you can use approximations, of course, but very often people in that case use simplifications and approximations. So one simplification, for example, is that you use this similarity graph G and partition it into k subsets, where k is another input parameter, and the partitioning also minimizes a function, for example, some function of the edge weights between and within the partitions. So the partitions are the clusters. The good thing here is that, well, that looks a little bit like partition clustering, like k-means. So you can use k-means, but you use k-means on the similarity graph. That's a huge difference, because the resulting clusters now may have arbitrary shape, which is in harsh contrast to classical k-means, which typically tends to have spherical clusters. And the basic algorithmic schema is that, well, each vertex, represent each vertex by a vector of its corresponding components and eigenvectors. So you do an eigenvector composition before, and then apply k-means on this representation that somehow represents or models this graph, the similarity graph properties. And then there are orthogonal to all those things are the hierarchical methods, where you want to reveal the hierarchical decomposition of a data. So if you have nested clusters, like one cluster, one concept, I mean, each cluster should stay or should represent a concept in real world. So you may have nested concepts. So one concept, one more general concept, breaks down in several more specific concepts. So you have a more general cluster breaking down into or breaking up into several more specific clusters, where the similarity is even higher. And in that case, if you want to reveal those relationships, you need to use hierarchical methods. Typically, the cluster hierarchy is represented by a tree-based representation. Dendrograms are the state of the art here. The whole thing is very closely related to the minimum spanning tree problem. We talked about that in KDD1. The key concept now is not only similarity or distances between points, but now you want to also compare clusters with each other. So you also need a similarity measure or distance measure between sets of points, because clusters are sets of points. One very popular thing is singling, complete linkage, and so on and so on. So here are the popular methods, the linkage methods, and also optics is quite common nowadays. Basic algorithmic schema is you typically start from the singleton clusters, which are the points of the data set, and those are the leaves of the dendrogram of the tree. And then you in each step you merge the most similar clusters until everything is in one cluster, and this is the root of the tree. So the root of the tree represents the whole database, and the leaves are the single points, and one inner node here represents all the subtrees, all the points in the subtree of this node. Yeah, so that was clustering, a very, very brief overview of clustering. And in the next podcast, we will have a very, very brief overview on classification. So stay tuned.